Now let us move on to the LAMMPS example to calculate the Fick diffusivity for a mixture of hydrogen and carbon dioxide at 50 megapascal and 323.15 Kelvin. The simulation box contains 60 molecules of CO2 and 60 molecules of hydrogen. In the previous video, I did not show you the geometry and the topology of the molecules of CO2 and hydrogen. Thus, before we begin this demonstration, let us first have a look at the two different molecules. As I have mentioned before, carbon dioxide is taken from the Trappe force field. In the Trappe force field, CO2 is represented as a rigid dumbbell, with the central atom being carbon, flanked on the two extremes by oxygen. The distance between the carbon and the oxygen is 1.16 angstroms. The partial charge of carbon is positive, with a charge equal to 0.7 times the electron charge. The partial charge for oxygen is minus 0.35 times the magnitude of the charge of an electron. Overall, the molecule maintains charge neutrality. All three molecules are centers for Lennard-Jones interactions, and they also participate in electrostatic interactions. For hydrogen, we have used the Marx force field. In the Marx force field, we have the two big hydrogen atoms on the two extremes of this rigid molecule, with a dummy molecule in the center. The distance between the dummy molecule and the hydrogen atom is 0.37 angstroms. The dummy molecule is responsible only for the Lennard-Jones interactions of the entire molecule. Note that the hydrogen atoms flanking the rigid dumbbell do not participate in the Lennard-Jones interactions. The hydrogen atoms on the other extreme only participate in electrostatic interactions. With this as a starting point, let us now move on to the demonstration of calculating the Fick diffusivity using the LAMMPS script. To show you the data point that we are trying to reproduce, I'm looking at the pressure of 50 megapascal, 323.15 Kelvin, and an equimolar mixture of carbon dioxide and hydrogen. Note that the properties can be found in the Excel sheet transport properties H2CO2. To calculate Fick diffusivities, I have already mentioned that we begin by calculating the Maxwell-Stefan diffusion coefficients which takes into account the cross correlations of the molecules of type A and B, where A here is hydrogen and B is carbon dioxide. To enable the calculation of these cross correlations, I'm using the OCTP module, or on the fly calculation of transport properties module, developed by the engineering thermodynamics group here at TU Delft. Thus, one has to first install these modules to the LAMMPS source files, which should then be compiled to give you a new LMP serial file. Let us first do this. I will open the browser and type OCTP. Since I have already browsed this for many times, it shows up as the first link on my browser. So this is the article in which the OCTP module was developed specifically for the calculation of transport properties using the order n algorithm. The order n algorithm is described in detail in the textbook by Frenkel and Smith, and is thus not discussed here further. For a clearer description of Maxwell-Stefan diffusivities and also Fick diffusivities, kindly also refer to this article. Now, to install this particular module, we open the supporting information of this article. I scroll to the end of this article, which provides all the details. Here is a description of how to install this module into your LAMMPS source directory. Let us follow this step by step. We first go to the home directory of LAMMPS and into the src folder within the LAMMPS directory. In our case, our LAMMPS directory is situated in this particular folder. So we are now inside the source directory. The file next instructs us to pull this particular set of files from this GitHub repository maintained by Othonas Moultos from the engineering thermodynamics group. So let us run this command. So here, my computer warns me that I've already have this file installed. So let me try to redo this for purposes of instruction. As you see, once I do the git clone, all of the files have now been pulled into my src folder. And to verify this, we can try to see that it in fact exists here. So these are the contents of the OCTP folder. The next step is to copy all the CPP files from the OCTP folder into the SRC directory. So let us do that. So copy all the star.cpp into the current folder. Since I've already done this before, it is asking me if I want to overwrite this. I wish to say yes. And similarly, it also instructs me to copy all the .h files into the current folder. Now, finally, I have to make these files to generate a runtime file. But before that, let me first remove the LMP serial file so that we can generate and I can show you that this works for us. So let me do make serial because we are interested in generating a serial executable for the LAMMPS. So these are warning messages which you do not have to worry about. And finally, I have an executable called LMP serial. And you can also see the timestamp on this file to verify that it is in fact being generated at time 10:28 on May 29th. As you can see, it's 10:28 on May 29th. All right, so let me go back to my initial folder. The input script that instructs LAMMPS to calculate these cross correlations responsible for the Maxwell-Stefan diffusivities is written in the input script called fick.in. So let me open that. So I will not go through all the basics again, since we have already done this in the previous example. I only wish to show you the more recent additions into this particular file. Note that we had performed NPT simulations, which was up to this point here in the previous script, up till line 204. Once we have a stable pressure and once we have the density of the box fixed, we next have to fix the box size. So in the NPT phase, we determined what the density has to be, and the corresponding box size, which gives you the exact density, can then be calculated. And that is given by the variable box length final, which calculates f2 of 4. f underscore 2 basically tells you that this variable comes from the fix number 2, that is on line 198, and the fourth variable in this array. And the fourth variable in this array corresponds to the volume. So basically, the box length final tells you what should be the final length of the box, decided by the volume, cube root. Now note that the current box length does not equal to the final box length. And to approach the final box length, we have to expand the box. A sudden expansion of the box can lead to molecules trying to overlap with each other, which will result in your simulation to crash. Thus, it is instructable to expand the box at a velocity which allows your box to equilibrate in a smooth manner. To provide you a clearer instruction, I have written a statement here to print the current box length, the final box length that we wish to have in order to ensure we get a particular density. And finally, the expansion velocity of the box so that we have a smooth expansion. To determine the final or to determine the velocity of expansion, I have used this expression which tells you the distance over the time, which gives you units of velocity or in terms of angstroms per femtosecond. This basically tells the LAMMPS script to expand the box at these many angstroms per femtosecond until it reaches the final size or the final box size. Now I say LAMMPS to unfix NPT, which means that the pressure is no longer controlled through a barostat. Instead, I instruct LAMMPS to now initiate the NVT ensemble where the volume of the box is fixed, the number of the molecules inside the box is also fixed, and only the temperature is maintained through the use of a thermostat. And the temperature here equals the equilibrium temperature that we have set, which is 323.15 Kelvin. Finally, I instruct LAMMPS to expand the box to deform equally in the X, Y, and the Z direction at a velocity given by Vexpand or VEXP, which is available on line 211. I also unfix the previous thermoprinting statements, which is from lines 192 and 198. So in this brief period where the box is expanding, the temperature, density, pressure, and volume are not printed anymore, since it would not make sense to have these values since it is not an equilibrium system. Now, instead, what I print is the step, the potential energy, the kinetic energy, the total energy, the pressure, and the dimensions of the box, the lower limit of X, the lower limit of Y, the lower limit of Z, and also the upper limits of X, Y, and Z. Now I run the simulation, which will now expand the box. After the statement has finished, or after LAMMPS has executed line 231, my box should have reached its final dimensions, which means the box length final is equal to my current size of the box. Now I instruct LAMMPS to unfix box expand, which means that the box size is not changing anymore. With this fixed box, now I repeat the same procedure that I did for the NPT where I have a pre-initialization to equilibrate the system for this temperature. I start with a very small time step of 0.001 and I increase it in orders of magnitude of 10 until I reach a time step of 0.5, and I perform a series of intermediate simulations in the so-called pre-initialization step. This allows the system to gradually relax towards equilibrium and also attain the temperature that we wish to equilibrate it at. Finally, we perform an NVT initialization where I have performed it with NI NVT steps. To look at the values of these variables, they have been defined here at line 34, 35, and 36. Once I finish initialization, I will now run the production step where I will run a longer simulation within the NVT ensemble. And during this production run, I will obtain the total average energy. For the sake of bookkeeping, I will reset the time step to 0 before I begin the production run. I initialize 3 variables called TE1, which equals the E total or the total energy, which equals the sum of the potential and the kinetic energy. I initialize a variable called KE1, which equals the kinetic energy, and then PE1 equaling the potential energy. I have 5 different fixes, and these fixes essentially calculate the average quantities of temperature, total energy, kinetic energy, and potential energy. The main reason behind calculating these quantities is that we finally wish to calculate Fick diffusivities in the NVE ensemble. The advantage of performing these computations in the NVE ensemble is that you avoid artifacts related to the interference of the thermostat with the dynamics of the molecules affecting the overall diffusion coefficients. Thus, it is good practice to always switch off all your thermostats and barostats before measuring your diffusion coefficients. But in order to do that, and to ensure that you are in fact at a pressure and temperature that is desired by you, you need to set the total energy such that it corresponds to a temperature. And for that reason, these quantities are first calculated. Now, I also define another fix to just calculate all the other properties such as temperature, density, pressure, and volume. I run the production run in the NVT ensemble, and I also generate a restart file, which is exactly similar to what we did during the NPT phase. Now, in the NVE, we need to set the temperature of the molecules since they're not equal to the equilibrium temperature that we wish to have. In order to do that, we now use the total energy, the kinetic energy, and the potential energy to rescale all the velocities such that they correspond to the equilibrium temperature that we wish to simulate the system at. These two commands here finally achieve this goal where the velocities are rescaled such that the temperature of the system now equals exactly to the equilibrium temperature that we desire, which is equal to 323.15 Kelvin. Now I unfix all of the variables shown here that were used for the calculation of this new temperature. And I also delete some of the variables that were used for the previous purposes. Notice that now I have unfixed the NVT phase, and I fix now the rigid NVE phase. It is noteworthy that now I do not specify a temperature or a pressure since there are no barostats or thermostats affecting the dynamics of the molecules in the NVE phase. This is also the phase that is native to molecular simulations. Finally, I run now the system in the NVE phase with an initialization just to relax the system into equilibrium. The relaxation to equilibrium is necessary since the velocities of all the molecules have been rescaled. Now, we enter the production phase for the NVE. This is the phase where we begin to calculate the diffusion coefficients for these mixtures. Once again, for bookkeeping, I reset the time step to 0. Once again, I also initialize variables temperature, density, pressure, and volume, which are then periodically outputted into the thermo nvt.out. It would be more suitable to call this thermo nve.out. As I specified to you before, the cross correlations accompanying the calculation of the Maxwell-Stefan diffusivities are enabled by invoking the OCTP plugin, or on-the-fly calculation of transportation plugin, which we have now installed. To calculate the Onsager diffusivities, as you know, more appropriately, I would call this Onsager coefficients and not diffusivities, which then contribute to the Maxwell-Stefan diffusivities. I apologize for the typo here. Now, the important issue or the important thing to consider here is that you need to input the position of all the molecules to the OCTP plugin. For this reason, you have to instruct LAMMPS to provide or first accumulate all of the positions of all of the molecules. And this is done by the compute command. So here I say compute pos all position. Now, an important thing is that we have to specify how to specify the position of the molecules. Now, we do not wish to compute the position of all the atoms in a given molecule. For example, if I'm considering a CO2 molecule, it would suffice to have only the position of the carbon molecule. Similarly, it would suffice only to have the position of the dummy molecule in the hydrogen model. To ensure that only the positions of carbon and the dummy atom are accumulated during this compute, we have to specify something called as groups in the LAMMPS input script. And this is done in line number 114, where we describe something called as a group. I call the group as carbon or carb, where I only track atoms of type 1. So remember that in the CO2.txt, my type 1 corresponds to the carbon atom. So essentially, I'm creating a group where all the carbons are then accumulated, which are within the carbon dioxide molecule. Similarly, I create another group called high, corresponding to the hydrogen, where I track only molecules of type 3. It is not completely true that I call this high, but rather call it dummy, because I'm truly tracking the dummy atom in the hydrogen molecule. To enable the computations from the OCTP plugin, it is crucial that these groups are clearly specified at the beginning of your simulation. If the groups are not correctly specified, the OCTP plugin fails to recognize which positions to compute and could thus result in a crashing of your simulation. So once you now know how to calculate or how to accumulate all the positions using the compute, you can next instruct LAMMPS to perform the cross correlations required for the Maxwell-Stefan or the Onsager coefficients. Let me once again show you what the Onsager coefficients are. The Onsager coefficients are precisely these cross correlations between molecules of type 1 and molecules of type 2. Kindly notice that there is a typo here, that this should be molecule 2 rather than molecule 1. So these are the cross correlations that we are interested in, and this is what is computed by the OCTP plugin. The results of these plugins are then outputted to the thermo folder. The key inputs here are the parameters ndiff, nwrite, nb, nbe, the details of which are clearly specified in the original article that can be found here. So I urge you to go through this article to clearly understand the different values of these parameters. It would suffice for you to use the parameters that I've currently used. For now, I will not concentrate on the calculation of other properties, but it is indeed possible to also calculate the shear viscosity and bulk viscosity as well, since all of these calculations only require cross correlations and correlation functions. It is also possible to calculate the radial distribution functions using the OCTP plugin. But once again, I refrain myself from delving into the details of this calculation. For further details, please refer to this article that I show here. Now, once these parameters have been set in, the final step is to instruct LAMMPS to run a production in the NVE phase. In view of statistical accuracy, it is extremely important that you run very long simulations so that you get reliable and accurate results for the Fick diffusivities. Now, I will not run once again these simulations because I have previously done this, and I just wish to show you the output file. Note that we have run this for quite a long time. As you can see, these are roughly 2 times 10 to the 6 steps. And what you see here is the potential energy, the kinetic energy, which has to be positive, and the total energy. Notice that the total energy is extremely stable, and the variation only happens in the 4th digit. That is the digit after the decimal. And this has successfully run, and it took me 3 hours 41 minutes to run this entire simulation. But be reminded that it is not guaranteed that your Fick diffusivities have already reached or become stable. Now, to extract the Fick diffusion coefficients and also the Maxwell-Stefan diffusion coefficients, I urge you to read the manuscript that was shown here, and also several other manuscripts that are mentioned in the readme.docx manual shown here. In particular, it is clearly mentioned how to calculate these, or how to identify regions of convergence in article number 7. The main purpose of this document or this video was to show you how to calculate or how to run the LAMMPS input script to obtain the output file which corresponds to the different diffusivities, the Maxwell-Stefan diffusivity in particular. Note that you finally only have the Onsager coefficients, and the Onsager coefficients are printed in the following format, where you have the time and you have the mean square displacement corresponding to carbon-carbon, carbon-hydrogen, and also hydrogen-hydrogen. And as I've shown previously, the ik here then can be where I is carbon and k is carbon corresponds to the first column. I is carbon, k is hydrogen corresponds to the second column. And then hydrogen, hydrogen corresponds to the third column. Once you know the Onsager coefficients, so the way to extract the Onsager coefficients is to plot the first column and with respect to the 0th column, and identify the region where the slope is 1 in a log-log scale. And once you have identified the region where the mean square displacement varies linearly with time, the slope then gives you the omega cc. Similarly, omega hc can be identified by plotting the MSD as a function of time and identifying the region where the slope varies linearly with time. And the resulting slope can then be extracted to give you lambda HC. And this happens usually in the long time limit and hence is given the terminology limit t tending to infinity. And the d by dt tells you the slope. Finally, the same procedure can be carried out also for the hydrogen. Once this is done, you can combine the Onsager coefficients obtained from the mean square displacements of carbon-carbon, carbon-hydrogen, and hydrogen-hydrogen together with these ratios that are input parameters in the simulation to finally give you the Maxwell-Stefan diffusion coefficients obtained from MD simulations. Please be mindful that these Maxwell-Stefan diffusion coefficients have to be corrected for finite size effects through this relation. The size of the cubic box is already known from your simulation. The temperature is something that is set. The thermodynamic factor to derive it, we've already discussed that. Finally, we can also extract the viscosities in a manner similar to what is shown here using the OCTP plugin. Of course, I have not instructed you on how to calculate the viscosities, but this can be done in a procedure similar to the Onsager coefficients. For this, I once again urge you to read the article for this particular manuscript. Once you have corrected for the Maxwell-Stefan diffusivities, you can multiply this with the thermodynamic factor to finally obtain at the Fick diffusion coefficient. With this, I hope to have provided you an introduction into multi-component mass transfer relevant for underground hydrogen storage. In this video, I have talked to you about the two main formalisms to describe mass transport, which was the Fick diffusion coefficient and the Maxwell-Stefan diffusion coefficient. Finally, we also looked at how to calculate the Onsager coefficients and finally the Maxwell-Stefan diffusion coefficients using cross correlations in LAMMPS. To enable calculations of these cross correlations, we have used the OCTP plugin developed by the Engineering Thermodynamics group at TU Delft. Finally, I leave it to you as an exercise to then extract the Fick diffusion coefficients or to first calculate the Maxwell-Stefan diffusivities from the Onsager coefficients and then combine it with the thermodynamic factor to obtain the Fick diffusion coefficients. Thank you for your attention.